Hello everybody. So in this video we are going to see how A star algorithm works. So if you see A star algorithm, what is that? First of all, we'll see. It's an informed search algorithm. It's an informed search, unlike Dijkstra's algorithm or a BFS, breadth first search, or a depth first search. This is informed. That means it uses heuristic. Heuristic is some extra information. This is said to be some extra information to find the path. So it finds optimal path. Like Dijkstra's, it also finds an optimal path. But it takes less time compared to Dijkstra's algorithm, which is said to be uniform cost search algorithm. So it gives a decent average case search time complexity. What is search time complexity? The time taken to find the optimal path is called search time. So it gives a decent average case time complexity for search time because it is somewhat brainy because of this heuristic nature. So before getting into the problem solving, let us see what is heuristic and why that heuristic is leading us towards optimal path. So if you take heuristics mechanism, we have to make sure that the heuristic should be admissible heuristic. So what is admissible heuristic? Let me tell you what is admissible heuristic. We need admissible heuristic to solve A star algorithm. So in our case, if you take the source node is A and destination is Z, so straight line distance between any node to that destination is called heuristic. So for example, this is 18. This 18 is said to be heuristic value, and this is a straight line distance from D to Z. And this 8 is the straight line distance from F to Z. The same way, 5 is the straight line distance from E to Z. 14 is the straight line distance from B to Z. So every node has to have this straight line distance. So that straight line distance is heuristic. We need to have a straight line distance between a node and a destination. This is needed. This we say is heuristic and it should be admissible. What is this admissible is? So if you say h of b, okay, so that's a node b. Heuristic of b is actually 14. Okay, when you say some heuristic, it's admissible. The actual cost from b to z should be more than or equal to 14. Okay, so it should be more than or equal to the heuristic value. So actual cost, if the actual cost exists to go from B to Z, actual path cost, if the path exists, there will be a cost for that path. That path cost should be more than, actual path cost should be more than or equal to the heuristic cost, which is 14. You see here, if I am going from B to Z, so it is 11 plus 5, which is more than 14. It is 16. 11 plus 5 is 16, which is more than 14. If you take some other route also, I go from B to E to C, then C to F and Z. That's also more than that. So whatever the route you take, that should be greater than or equal to the heuristic cost. So that is proved here in our case. Why we say straight line distance between a node and a destination or between two nodes is the shortest distance between that one. We have a proof for that. Pythagoras proof is all available. So the proof says if you have a straight line distance between 2 points, so for example I have 2 points, point A and I have point B. 2 points I have. This coordinates are A comma B, this B's coordinates are C comma D. So what is the straight line distance between these two is, we say a difference c, okay, square it, a minus c square plus b minus d the square root. So it's just application of Pythagoras. Okay, so here we just find this one and this one and we do that. So this is the distance. So this distance can be found out easily. We don't need a root for this. If you are just given a coordinates, latitude, longitude for a place, and you can easily find out the distance between these two by applying this simple formula. So these are all proved things. So this is proved that if the 2 points are there and if the straight line distance between the 2 points will be smaller to all the routes that is taking some other path, say if I am coming from some other path to B, A to B like this, whatever the path you take, it will always be more than the straight line path. So this is A, this is B, this is C, this is D. Okay, this is cost of going from here. So this will be smaller than these distances, total distances. B is the total distances if I come via certain point. If I come via this point, C is the total distance. So this is proved. So in our case, we have a heuristic which is admissible. Okay, so we have a admissible heuristic. Admissible heuristic is needed for making sure that whatever the route we are finding is optimal. So that is needed. Okay, now you see, we'll take this problem. The source node here is A, so this is the source node and the destination is Z. That's the destination. So as per this AF star algorithm, we say f of x is equal to g of x plus h of x. For every node we will be finding. So for example, if I am in node B, we will be finding what is this A star's function value from B. It's nothing but the g of B plus h of B. This is heuristic of B. This one is said to be distance from source to that B value. Okay, so the g is distance from source to node B. This is heuristic. Straight line distance from B to Z, from B to Z, which is the destination. So this is 14 here, so that is heuristic. So this value is 14 here. And what is G to GB is to come to B from source. What is the cost? 9. Okay, so that's how we calculate the A star's value. And what it says, let us understand. 14 plus 9 is 23. So now if I say, if you go via B, so F is equal to 23. The meaning is, this is 14 plus 9. So when you take a path of, if I say A, and if you go via B, it will take for minimum, okay, so at least distance, at least you can say, at least 23. Cost will take, or I can say minimum it will take 23. So minimum it takes is 23. You cannot go to Z if you pass through B. If B is part of the final path as a node in that path, the minimum will be 23. If A from source and if via B, if you pass through to reach the destination, minimum it takes 23. That means if there is a next node comes, okay, in that path to reach the destination Z, it will never be less than 23. That's the meaning, because of that admissible heuristic. Okay, so this cost is fixed, 9, 11 and all, it's fixed. The heuristic is only is our some guesswork we are having, or that's the extra information. So it is admissible, so that is why this is maintained. So if the minimum is from here 23, if you go to this one, it will not become 19. Meaning, so if I go to B to some M node, if we take this root of M, here you are saying if you pass through B, it is at least minimum it takes 23. Now suddenly it will not change to 19 because of admissible heuristic. It will be more than or equal to 23. That is possible. So it can be 119 or it can be 23. That is possible, which is 23 is equal to this one. Okay, it can be 191. So that is possible. So whenever you find the minimum cost to go to destination from B, it will take 23. Okay, so that means the next coming will be more or equal to this A star's function value. Okay, so based on that, if we move, we will be arriving at the optimal solution. So this is a greedy property. While solving this problem, I will explain you more. You will understand at that time in a different way. So now we have this graph. As I told you, we're going to solve it. Source node is A. What's our source node? A. What's our destination? Destination is Z. I have to go from A to Z. So we have this information already. In Dijkstra's algorithm, we will not have this 21, 18, the one put up in the red color. The heuristic value will not be there. So we have 14, 21, 18 and 8 and 5. We have these values. We have these values here, 14, 21, 18 and all, which is a heuristic value, but we have 9, 4, 17, which is a path cast. In Dijkstra's, which is a uniform cast search, we will not have this heuristic value. So this is informed search algorithm. That's why we are having this here. So now we are going to proceed. Now since you are in here A, I am in A, where I can go from A, I can go to B, okay, and I can go to C, I can go to D. So we have to find the path F for B, C, D. So what is F of B? F of B is equal to G of B plus H of B. So here G of B is what is G of B? To reach B, what is the cost? It is 9. Okay, H of B. What is the heuristic from B? It is 14. So 14 plus 9 is 23. So here it is 23. So it is 9 plus 14 is 23. If you go Y of C, it is F of C. F of C is equal to come to C is 4. Okay, so G is 4. To go from C to Z, C to Z in a straight line distance is 18. So heuristic we have 18 is the heuristic, so it is 22. So here it is 22. And if you go to D, so F of D is, to come to D it is 7, from D it is 18, so it is 25. So we got 25 here. So heuristics are given. So now what it is saying, if you take a path of B, okay, path which is having B, at least 23 will be there. More than will be there once we are expanding the path. More or equal to 23. Here we say, if you take a path of C, it is more or equal to 22 cost. Here you are saying, if you take the path of D, it is saying it will be more or equal to 25. So out of these three, I am going to take 22 because I am greedy. So it is saying at least 22, minimum 22, but this is saying minimum 23. So it doesn't mean that if I take the path of C, I will be having the optimal path via this one. There is no guarantee for that. As of now, it is saying 22. But when I expand, sometimes the next coming node might be just behind this C. Who knows? Here the E is in the right side of C, which is towards Z. But if the case where E is present here, we might not be having the good straight line path from E to Z, but in this case it is next to C. So that's why I'm saying, if you take the shortest route, it does not guarantee that you are gonna get the optimal path that is passing through C. There is no guarantee for that because of this heuristic. But we are taking this one, we are greedy, and we think that if it is existing, the optimal path is existing, it is having a good probability that it is present in this one, because as of now this is best. So I'm going with the probability of the optimal path being present. If I go via C is more, that is why I'm going towards this thing. Okay, so now we are taking the route. So first of all, if I expand this, so first initially we were in A, and if I am going to B, it is 23. It's saying this is 23 cost, at least minimum 23. If you go via C, minimum 22. If you go via D, it is saying minimum 25. We are just expanding. Now we are taking C. So we're going to expand C. Where C goes to E. So if I'm expanding C, f of E. So if I go via E, because C is connected to E. If I go via E, what is the cost? What is the G? G is, to reach E is 4 plus 17. 4 plus 17 is 21. And from E, if I reach Z, it is 5. That is heuristic. So here, to reach E from source, you have to consider. So that means 4 plus 17 is 21. That's what this is G of E. This is H of E is 5. So this is 26. So here I am going to put F is 26. Or we will expand and put it here. So when I am expanding C, I am getting to E, which is having a F value of 26, and C is going to F also. So function of F is, what is the cost to reach F is 4 plus 12, 16. That's a G of F. F of F, or H of F is 8. 8 is the heuristic. So 16 plus 8 is 24. So this is 24. So if I go to F, it is 24. Now we are analyzing. We have 25, 23, 26, 24. So now what to expand? Now it is saying, E is saying, if you go via this E, that is ACE, minimum 26. After that, if you expand, I don't know, it might be more than 26 or equal to 26. There's no guarantee for that, but it will be more or equal to 26. Here it is more or equal to 24. Here it is saying more or equal to 23. Here it is saying more or equal to 25. But which is the best to expand from? Now I will expand from B, because it is saying 23. So immediately I may reach a destination, who knows? So I might get a good chance of reaching the destination compared to going via these things. So we are selecting the smallest. So we're going to expand B. We're going to expand B. Where B goes? B goes to E. Okay. So if I expand B, B is going to E with the cost. So what is the cost of reaching E when you're expanding B? That means 9 plus 11, 20. Okay. So F of E, when I'm expanding B, we are expanding B now, is equal to 20, which is the G of E, plus from E, what is the cost? Heuristic is 5. So it is 21, 20 plus 5, it is 25. So this is 25. Okay. Now where else B goes? Nowhere else. Okay, so it is, so as of now 25, 25, 26, 24. So out of these one, now this part is promisable. It is saying at least 24 it takes, which is the minimum of all others who are saying this 26, 25, 25. So we are going to expand F, this F. We're going to expand this F. So this F, where is this going? This F is taking me to Z. Okay. What is the cost of going to Z? Via is F. That means this is AC. AC is 4. 4 plus 12, 16. 16 plus 9 is 25. So 25. So if I expand F, I'm expanding F. The cost of going to Z is 25. Plus, what is the heuristic here? Z's heuristic is 0, because that's a destination. So it is 25. So now Z is 25. It is saying 25 here. Okay. So now if I take this path, that is saying 25. So now if you see, we have 25 here, 26 here, we got 25 here, we got 25 here. So these all still need to expand. We can expand that because we didn't touch Z here. This is a destination. This is 26. This is 26. The destination is Z. This is reaching the destination. Now we are just seeing the destination is Z. It is 25. Okay, it is 25. And if you take this E route, it is minimum 25. That means if I expand E, I may get more than 25 or equal to 25. But I already got one equal to 25, I reached this Z. Okay. And this is, it's minimum itself 26, which is more than what I got now. Here also it is 25. That means if I expand D, I'm not going to get anything less than 25 for sure. So that means this algorithm can be stopped. So when to stop? You just have to see all these values, other branches should be greater, like this 26, or equal to the one I reached. Okay, I reached 25 because it is equal to 25. So I'm not going to expand these paths. This is 26, which is more than 25. I'm not going to expand these paths. So I'm fixing. So A to C, C to F, F to Z. So the shortest path is you can go from A to C, C to F, and F to Z. This is the shortest path. So 4 plus 12, 16, 16 plus 9, 25. So we are able to get a 25. Okay, so this path is also A to C, C to F, F to Z. So now we got an optimal path. The search algorithm finds the optimal path. Okay, there is no other path which is less than this 25. There is one more path is existing, that's also 25. Here you see it's 25 because if I expand E, it will be reaching Z. Okay, with the same cast, but we didn't do that because we reached that one. So the algorithm stops here itself. So it is giving an optimal path. I hope you understood. Thank you.